Hello and good morning, everyone. Today, inshallah, we will continue with differentiability, as I told you. This is related to the topic that we already initiated last lecture. Okay? Yes, I need to check that my phone is open because I have an exam at the time being with your companions in FCT. So once more, we will go through differentiability. I will start this lecture. Of course, I will try to cover the differentiability, different probabilities of differential functions and differentiability in R and in Rn. Hopefully, we will be able to cover this part. If not, we are very good because we already covered the directional and higher order derivatives in the previous. So we are ahead of Lisbon at the time being. We are not behind them. So we are supposed to be, we are in a very good shape, inshallah. Okay, once more, all of your course notes, references, everything you will find in the model. Also, you will find a couple of recorded vids about this session, also on Moodle, plus this live recorded lectures, you will find them on my YouTube channel as usual. Also, I sent you the PDF of this lecture, I believe 2 or 3 days, I think yesterday, maybe yesterday. Okay, in this session, we will go through the definition of differentiability in R or in R2 or in Rn. All of them, they are really essential and very close to each other. And let's see how we start. First, I want you to remember the total derivative. Okay, the total derivative or the main derivative formula, it's used when we are dealing with from R into R functions and single valued functions. And usually, it is the rate of a change of the output relative to the change in the input. This is exactly what's happening. I'm getting the difference in the output relative to the difference in the input. And as we did go through this in the previous session, the slope is rate of the tangent at any point. It's really very simple. It's just only the difference of f of x minus f of a divided by x minus a. And that's what we call it a derivative. So f dash at certain point equal to the limit of x tends to a of f of x minus f of a over x minus a. This equation is really very important because also if I know the derivative, I can use this equation to speculate or to approximate the value of f of x. So for example, if I have f dash at a, which is equal approximately to f of x minus f at a, and if we multiply both sides in x minus a, as you can see, I can say that f of x is equal to f of a, once you move this to the other side, f of a, plus f dash at a times x minus a, which mainly the equation that we use to find a straight line relative to the derivative if it exists, and that's mainly the main equation that we will depend on. Of course, this value is an approximation. Ahmed, please be careful. Okay, طبعا it's an approximated value. علشان both sides are equal to each other, لازم to add a remainder term of x, as you can see. This is mainly the main equation that I can use to find an approximation near a certain point using derivative. And as you can see, Omar, it came from the definition of the derivative by itself. So once more, that's the main derivative formula. So if I want to get f of x, it's simply I'm multiplying, making cross product and rearranging terms. I will have this equation which will appear in the coming slide in details. So once more, the derivative, it is the ratio of a change of the output relative to the input of your function. And that's the definition. Also, I can write the definition as we saw in the previous session, which is limit h tends to 0 for f at a plus h minus f of a over h. And that's the general definition that we used mainly to prove the existence of derivative of certain various functions, either in one variable or in multiple variables, and in this case it will be a partial derivative. Okay? We will go through it inshallah shortly. So once more, I want you to remember this equation. If I reordered it, I will get the condition for differentiability. So I can redefine all of this as the following. The function f, which is running from R into R, is differentiable at a certain point. That's the condition for the differentiability, at a certain point. If in a neighborhood of point A and f of A, I can approximate the value, or I can have an approximation. So one may write approximate the value of f by the value of the line. If you look to this equation, as we just did, you will find that I can find this equation simply from this guy. Just reorder it, get f of x. You will do a cross multiplication, moving f of a to the other side, and we will add r of x minus a, which is the error term, or the remainder term, to make the value of the function equal exactly the approximated value at certain point. Okay? So once more, that's f of x. Such that in order to make this equation valid and perfect, it's supposed to be the rate of decay of the remainder term should be decayed faster than x minus a. Or simply, the limit of r x minus a over x minus a should equal to 0. Yani, should exist and be equal to 0. In this case, the approximation is 100%. And in this case also, it means the function is differentiable. So actually, if r of x is equal to 0, now you can approximate the value, not approximating, you are getting the values of the function exactly. Okay? So once more, how to check the differentiability at certain point? All I have to do is to try to rewrite the equation in this manner, and then evaluate the value of the limit r of x minus a over x minus a, and prove that, or find the value of the limit that is equal to 0. Once this relation approved, then this approximation is valid without r because it's equal to 0, so the derivative already exists. So once more, the differentiability at a certain point, we will check this relation, and when r of x minus e is equal to 0, which means the function u function is differentiable. Okay, as I told you, this is the approximate error, and once more, it makes sense. See, if r of x minus a divided by x minus a, and it is decreasing while x tends to a, so once you move in this direction, the value of the approximation will be exactly equal to the value of the function at this point. This is how to prove that the function is differential. If I want to find, ya Ahmed, a tangent to a curve at certain point, all I have to do is to write this equation. So if I want to get a tangent for a certain function f of x at point A, all I have to do is to get the value of the function at A, then get the derivative at A, multiplying it by x minus A. That's the equation of the tangent for the curve at certain point. Okay? Okay. Then, once more, the differentiability, or f is differentiable if and only f dash of a is finite, means derivative exists and is defined. This is the definition of differentiability. Proposition, if f is differentiable at a, then f is continuous at a. That's really very important definition. So, if the function is differentiable, it is continuous. But remark that the continuity is not a condition for differentiability. Do you read what I'm saying? So, if the function is differentiable, it means it is continuous. But it is not a must. If it is continuous, it will be differentiable. Okay, let's test this function. He is asking you, show that f is differentiable in R, and giving you the equation or the function to be tested, f of x, which is a function defined on more than one domain. It is e to the power of x minus 1 if x is greater than or equal to 1, and 1 plus 10x if x is greater than 1. Okay? Leave this expansion. I will tell you what are we going to do with it just shortly. I want to start with the differentiability. So all I have to do, we will begin by finding the first derivative of f in order to use it to write the equation of tangent line, as you saw. So the first step is to try to get your partial derivative. Once we are to get the derivative. So for x less than 1, f dash x will be the derivative of this guy, which is the function by itself, because it's an exponential function. It's going to be e to the power of x minus 1 times 1, which is e to the power of x minus 1. And once you try to differentiate this guy, the derivative with respect to x, this is going to be 0, and that one will be 1 over x. So that's f dash in the case of x greater than 1. After getting those derivatives, remark, since f of x at 1 is defined by more than one function, we must use the definition, because you can't define the definition of this function. In general, it is defined in more than one domain. Okay, it's a piecewise function. So I will start using the definition. So, because this is not just only one function, okay, I can differentiate, but in this case, I will use the definition in order to prove my point of view. The definition will state that the derivative will be f of a plus h minus f of a over h. But here I'm studying the case when the conjunction is happening at 1. So instead of having f of a plus h, I'm studying at 1 plus h. Minus f1 over h. So this is exactly the limit that I want to examine. But Mr. Ahmed, I have a problem at 1, because the value of the function is defined by exponential form when x is less than 1, and by logarithmic function when x is greater than 1. This is why I will have to apply this law how many times? 2 times. The first time it will be from the right hand side. So I'm talking about the period where x is greater than 1, or the interval where x is greater than 1. In this case here, Omar, instead of having f1 plus h, I will use this guy, which is going to be 1 plus len of 1 plus h. This is the value of f of x. Minus the value of the function at 1. Once you put x equal to 1, it's going to be 1 plus 0. So once more, Ya Ahmad, this is the function, and that's 1, which is the definition or the value of the function at 1. Okay, I will show you that this value is equal to 1. It's very, very simple. I will erase negative 1 with positive 1, and we know one of the famous laws of limits, len 1 plus h over h when h tends to 0 is equal to 1. I will show you from there. Okay? If I want to go to 1 negative, it's going to be exact. Okay, let me do it. I was going to say the negative first and go through the details of how we evaluated the limit, but let me do the limit just short. Once more, I need to evaluate limit h tends to 0 for the function of len 1 plus h divided by h. It's very, very simple. I will use Maclaurin expansion. Maclaurin expansion for len 1 plus h, this is the expansion or the approximation of len, which is going to be h minus h squared over 2 plus h cubed over 3 minus h to the power of 4 over 4, blah, blah, blah. All of this is divided by h, and that's the limit of h tends to 0. As you can see, I can take h as a common from all denominators. Am I right? If you took h as a common from all denominators, you will have h1 minus h over 2 plus h squared over 3 minus h cubed over 4 plus blah, blah, blah. All of this is defined by h. Then both of them, they will be cancelled with each other. And since you have the limit of h tends to 0, so all of these terms also will be cancelled. And so the limit will equal to positive 1. This is why the limit of 1 plus len 1 plus h minus 1 over h, when you cancel and simplify, is going to equal to 1. Remark, this is half of my limit, because I will have to continue. Okay? This is the case when I'm dealing with the interval greater than 1. When I'm dealing with the interval less than 1, Mr. Ahmed, I will have to use the exponential form. So once more, this is going to be e to the power of 1, okay, plus h minus 1. Okay, so once more, just in a second. Of course, the explanation of the logarithmic function, I've wrote it here. Okay? This is how it is cancelled with each other. Once more, that's for the negative part, as I told you. This is e of x minus 1. I will replace the x by 1 plus h. So it will be e to the power of 1 plus h minus 1. And once more, negative 1 will eat positive 1. And you will have e to the power of h minus 1 divided by h. Am I right? Once more, Mr. Omar, use the expansion. Can you see the expansion? I can use this expansion. If you expand e to the power of h by this guy, it will be 1 plus x squared over factorial 2 plus x cubed over factorial 3 and so on. All of this minus 1 and divided by h. Of course, all of these are h values. The positive 1 will eat negative 1. And also take h as a common. It will be eliminated with the denominator. Take h equal to 0, so you will have the same exact result. Those two examples of the limits are famous ones. So down the road, once you see ln 1 plus h over h, the limit is equal to 1. And also, e to the power of h minus 1 over h, e to the power, once more. Just in a second, if I saw ln 1 plus x over x, limit x tends to 0, the result is 1. And also if I have limit x tends to 0 for e to the power of x minus 1 over x, the value is also equal to 1. This is from way, okay? Bye, Mr. Omar, bye, Mr. Ahmed. So now from these two facts, I have the first derivative which is equal to 1, because the left-hand side, the right-hand side equal to each other. So the first derivative is equal to 1. F is differentiable in R. Once you are studying the differentiability of this function at the point 1, it is continuous and differentiable, as you can see. Now, if I want to discuss once more, he is asking you for each of the following parts. Ahmed, try to concentrate with me to get the best of the lecture. The presentation will be at what time?
2 but في مشكله في الباوربوينت اللي عاملينه بس.
طبعا. يعني امورك تمام يعني.
هو
في حاله نفسيه.
في مشكله.
For each of the following parts, state and justify whether the function defined by the indicated general expression is differentiable at A, and if so, estimate f at B using the tangent plan to the graph of f at A and f of A. عمر هو عايز تعمل رقم واحد, he wants you to show that this function is differentiable at the indicated point. يبقى انا هجيب ده عن طريق ال r of x minus e زي ما احنا شفنا. This is step 1. طيب step number 2, he wants you to evaluate the value of the function at B, at this value, using the approximation equation that we spoke about earlier in the first slide. طيب, let's do it together, step by step. The first step, I will go through the following. I will have to get the discuss the differentiability at x equal to 0, since A is equal to 0. So how to do this? I will get back to the main law. The main law will state that f dash at A equal to limit h tends to 0 of f A plus h minus f of A divided by h. But I'm studying here when A is equal to 0. This is why I'm using 0 plus h minus f of 0. f 0 plus h, so I will get back to this function. بص كده يا عمر, I will replace x by 0 plus h, I will replace x by 0 plus h. So my function will come to e to the power of h divided by h plus 1 minus 1 over h. Okay, once more, I'm taking h tends to 0. So once you take h tends to 0, it's going to be e to the power of 1, and this is 1, so it's just only e minus 1 divided by, once more, it's going to be 0 over 1, so e to the power of 0 is 1, 1 minus 1 is going to be 0, so your limit is going to be e to the power of 0, of course e to the power of 0 is equal to 0, so once you substitute, it's the same issue like previously, so the function will be e to the power of u minus 1 over u, and the limit will be equal to 1. Let me go through it step by step with you. The first step, I need to find f dash at 0, which is the limit of h tends to 0. For your function, this is your function, which is gonna be e to the power of h plus 0 divided by h plus 0 plus 1, and all of this is divided by h. In order to solve this equation, of course, minus the value of the function at 0, and the value of this function at 0 is equal to 1. So I need to evaluate this limit. In order to evaluate this limit, I'm trying to reach the form that I told you previously. Limit x tends to 0 of e to the power of x minus 1 over x. I need to see this guy. I need to have this function or this part is equal to that part, exactly. But unfortunately, Mr. Ahmed, I have h over h plus 1, and this is just only h. So I think one of the nice ideas to use is to multiply by 1 over 1 plus h and divide by 1 plus h. So I didn't do anything. Just trying to manipulate the form of the function to put it as near as possible to this form. Now, if I let uh over h plus 1 equal to u for simplicity, I will have e to the power of u minus 1 over u, limit u tends to 0. So once more, I'm dealing with this guy. So the limit of this part is equal to 1. If I'm getting the limit of that part, which is 1 over 1 plus 0, the limit also is equal to 1. So bottom line, all the limit is equal to 1. Okay? So the bottom line, the limit is evaluated is equal to 1. So once more, this is the function e to the power of x divided by x plus 1. I will use 0 plus h minus the value of the function divided by h, as you can see. Now I will make the substitution. It is e to the power of h divided by h plus 1 minus 1 over h. Now I know for e to the power of 0 is equal to 1. This is why this is equal to 1. Once more, I will try to use the value of the limit of e to the power of x minus 1 over x limit x tends to 0, which is equal to 1. In order to validate this, I will have to have the denominator equal to this value. So I need h over h plus 1 to exist in the denominator. How to do it, Ya Omar? I will multiply. Here, divide here by h plus 1, multiply 1 over h plus 1, exactly like what I did. In this case, if you remark, the value of the function in the denominator, it is exactly what's on the power of x. So now I can replace them by u. And this is exactly the limit that I am telling you about, that we saw previously. Which the result of this limit is equal to 1. But I still will have this guy, okay, in front of me. And this guy, there is no problem with it. Because once you do the limit of h tends to 0, this part will be terminated. So it is simply 1 times, it's going to be 1 times 1, as you can see. So once more, f dash at 0 is equal to 1. Now I need to evaluate the equation of the tangent. We can do it together. Omar, all I need to do is to substitute in the equation of the tangent. Y equal the value of the function at a, or I can write f of x is equal to f at a plus f dash at a times x minus a. Okay? I have everything. I have the derivative at 0, and I have the value of x and the a. So all I have to do is just to make a substitution as the coming step. So once more, this is f of 0, f dash at 0, x minus 0. Giant substitution. If I took this function and substitute instead of every x, so f at 0 will equal to e to the power of 0 divided by 0 plus 1, which is going to equal to e power 0, so it's equal to 1. So I will replace this guy by positive 1. Then I have f dash 0 already evaluated. So this guy is going to equal to positive 1. And this is just only x. So the result will be 1 plus x, as you can see.
Okay.
Now, I can get, after getting this equation, which is 1 plus x, I can get the value at b. So f at minus 0.01 is simply going to be 1 plus replace the value of x by minus 0.1, which is going to be 0.99. This is how to approximate. So the main idea is to find the first derivative of your function. After finding the first derivative of my function, I will start to evaluate, as you can see. If he didn't ask me to show the general expression in differentiability, or to show using the definition of differentiability, I can approximate also. Instead of all of this, instead of going through the limit and through the general terms, I can from the beginning. You know how to differentiate Omar. So I can, instead of all of this, if he asked me about the approximation, okay, or using the tangent line to the graph in order to evaluate the value of b, all I need to do is to get f dash at 0. How to get f dash at 0? I will differentiate this function. Omar, can you differentiate this function? This is, I'm sorry, just a second. This is f of x equal to e to the power of x divided by x and so on. Let's do the derivative together. So f dash x without the rho, it's going to be the exponential function, which is x of x plus 1, times the derivative of this part. The derivative of this part, which is going to be x plus 1 to the power of 2, then differentiate the denominator, which is 1, times the denominator, which is x plus 1, minus differentiate the denominator, which is 1, times x plus 1. Okay? So once more, if I'm trying to find the derivative of f dash x, it's going to be x plus 1 to the power of 2, then differentiate the denominator, which is 1 times x plus 1, minus differentiating the denominator, which is which is equal to 1, times the denominator, which is just only x, as you can see. So f dash at 0 will be e to the power of 0, which is equal to 1, times the positive x and negative x will eat each other. It's just only 1 divided by 0 plus 1 to the power of 2. So bottom line is equal to 2. Now I can approximate. I have the definition. So I will say that y at x is equal to f at 0 plus f dash at 0 times x minus 0. So y of x is going to equal to f at 0 substitute, which is going to be equal to 1, plus f dash at 0, which is 1, times x. So it can be approximated by 1 plus x. I need to find the value near origin, which is minus 0.01. So all I have to do is to substitute, and the result will be 0.99. So bottom line, I'm using the value at certain point times the derivative of the function times x minus 0. I had to use the limit, as you saw in the previous problem, because he asked me to use the definition. Or otherwise, the function need to be, the differentiability need to be discussed near that point. But the results will be exactly the same. So once more, this is the differentiability. I found the limit of h, the limit f dash at a, which is in my case at 0. It's going to be the limit of 0 plus h minus f of 0, and blah blah blah. Continuing this problem, you will find that f dash use the equation of the line, then make the substitution exactly as we did, then make give the value at approximate value at your number that you are interested in, substituting x by 0.01, and you will find your value. That's another problem. But also read carefully, okay, the problem. Here he is asking you, he's telling you, write the equations of the tangent lines to the graph of f at the point whose second entry, whose second entry is 1. So it means the y value is equal to 1. So I need to find the values, okay, of the function where y is equal to 1. How to do it? I will start by letting y equal to 1. So simply, Omar, I will put 1, which is y, equal to e to the power of negative x squared plus 2 over x. Of course, yes, you are correct. 1 is equal to e to the power of 0. Once the two bases are equal to each other, then the powers will be equal to each other, which means you will need to solve the negative x squared plus 2x equal to 0. Take x as a common, you will have 2 minus x equal to 0, which will lead to x equal to 0 or x equal to 2. So the solution when y is equal to 1, the x values are going to be 0, 2. Machine? Okay, I need the tangent plans at those points. It's very, very simple. So once more, the second entry is 1. Let's find the x values corresponding to this value. How to do it? I will take my function, inserting it equal to 1. 1 is e to the power of 0, so the power will equal to each other. Now I will need to solve this equation, which leads to in x equal to 0 or x equal to 2. Now I have the two values. The second step, let us now find the derivative of f of x at the first coordinates. دلوقتي اقدر اقول the first derivative. I can do the first derivative either by differentiating this function, okay, directly, or using the rule. This is f dash x, which is very, very simple, as I resolved the other problem. In order to solve this problem, in order to get the first derivative, it's simple. That's an exponential function. So f dash of x is equal to the same function, e to the power of negative x squared plus 2x, times the derivative of the power, which is negative 2 over x plus 2. That's the derivative of your function. This is f dash x. The second step, Omar, I will start to substitute with 0 and 2. I will use the substitutions. So once more, this is f dash x, negative 2x plus 2 times e to the power of negative x squared plus 2x. Then I will find the values of the first derivative at 0. So substitute by 0. This guy is going to be 0. And the power is going to be 0. So e to the power of 0 is equal to 1. 1 times 2 is equal to 2. Okay. Then I will find the value of the first derivative, but at x equal to 2. Once more, start substituting. So it's a negative 4 plus 2, which is negative 2. And for the power, it's going to be e to the power of 0, which is 1. So it's a 1 times negative 2, so the result is negative 2. I need to write the equation of the line. Can you memorize it? The equation of the line, it's f of a plus f dash at a of x minus a, which means if I want to write it at 0, so y is going to be f at 0 plus f dash at 0 times x minus 0, so it's just x. For the second point, it's going to be f at 2 plus f dash at 2 times x minus 2, which is going to be 2. For the first one, f dash 0 is equal to 2. And the f at 0, I will need to evaluate. Let's evaluate this guy. F at 0, which is equal to, so it's going to be 1 plus 2 over x. For the second guy, f at 2, start to substitute. Also, it's going to be 1 plus minus 2 over x. So those are the two straight lines tangent to your curve at when y is equal to 1. Of course, if there is a multiple choice, then you will check your results with the multiple choice that you have. So once more, the equation of the tangent at x equal to 0 is going to be 1 plus 2x, and at x equal to 2 it's going to be y equal to 5 minus 2x. It seems, yes, you will multiply negative 2 in x minus 2, so it's a negative 2x, and then negative 4 times negative 4, which is going to be positive 4 plus 1 is going to be 5. Okay? Okay, perfect. Once more, for this part, it's really very simple. All I have to do is to get my first derivative either by the definition or by the main rules. After getting the first derivative, I will use the formula. Y of x equal the value of the function at certain point plus the derivative at that point times x minus a. Okay? Here, there is a very good question, which is, if f has finite partial derivative at a, which means the partial derivatives really exist. If this will lead to f is differentiable at point A, the answer is no. We are not really sure. The answer is no. In one dimension, it is okay. Okay? If the function is, if the derivative exists, then it is differentiable and continuous. But in other than that, in R2 or in Rn in general, the general is no. We are not sure about this. Okay, how to be sure? Remember once more. This is f of x, f of a, and this is f dash a, x minus a times the remainder term. If you remember, in order your function to be differentiable, you will have to find that limit of x tends to a for r of x minus a by the magnitude, okay, of x. This value should equal to 0 by x minus a and so on. Which means the remainder term will be terminated, or will be erased, or will be infinitesimal. They call it a very small value, okay? Once x approaching a. So from this definition, that's the definition in R. If I'm talking about the definition in R2, then instead of the first derivative, as we saw in the previous lecture, we have the gradient vector. Omar, do you remember the gradient vector? The gradient vector is partial f partial x, partial f partial y. So mainly, it is the first derivative, but in functions, in several variables. So this guy is just partial f partial x, partial f partial y. And you have a dot product in x minus f, y minus d. That's the remainder. I will write this equation explicitly just in a second. So this is mainly, that equation is this equation. Okay? This is the value at a and b, once you are dealing with x and y. This is the first component of the gradient vector times x minus a. And that's the second component of the gradient